What if there were like the one that was you already put your yeah there. Or it's bags.
Yes. I think it should be posted now, actually. Yeah, it's yeah, there's like a quiz, there is an assignment, there is a lab. It's great. What?
That there's 3 assignments.
Just the one that matters though.
What? Yeah.
Yes.
Anything to do with your what about beta? Like I don't look on beta. I want you to say like yeah.
Yeah.
What is it? I could turn into Photoshop.
Have you done gradients in calc yet? Right. Yeah, you did, right?
We're about to do it.
Oh, you didn't yet? Okay. I'll tell you about it.
Apparently, I was totally confused.
Sure.
Sure.
Or you could just go on ChatGPT as well. Like, you know, I actually did, like, when I first taught 190 in 2021, I guess. I actually did like a whole thing about like gradients and neural networks. No. No, I did like I also kind of changed my mind about whether it's a good thing to do or not, because like it's essentially kind of like, do you need the broad details or like do you need the details, or do you just need kind of the broad strokes of how it works, and the details are already implemented 1,000 times anyways? And I think so, like when I started, I actually like coded up, like at my job, I coded up a neural network in C, well, C++. Because like in part because like there wasn't an open source package that we wanted to use, and we couldn't use something that didn't have the right license. But like that's not the case anymore. And I think kind of going down that particular rabbit hole doesn't make sense. But yeah.
Oh my God, guys, look, they got it here. Hello.
All right, there's a quiz. So let's start with a quiz. So are you here? Like I feel like the more we go into the semester, the more this is not an obvious question to answer. But okay, like here counts if you're on YouTube or just watching it later. Although I do close the quizzes like half an hour later. Anyway, so the second question, so we kind of discussed it, but I thought that it makes sense to talk about it explicitly, especially because like we're not done with dynamic programming actually, right? So is it true that anything that's doable with dynamic programming, when what you're doing is like you're computing some kind of array is doable in the same time complexity if you're using memoization? Anyone? Is it true? Who says it's true? It is true, or like close enough. So here's kind of the explicit transformation that you can think about, right? So let's say that we're computing like fib at 10. So one way to do it would be to say, okay, so, and then we define an array. So we'll define an array that's like this. And then we'll just compute it one by one. So we'll say, at 0 is equal to 0. We'll say at 1 is equal to 1. And we'll say this is okay. And then for everything else, we'll just compute it. And then at the end, we return a at 10. Right? So that's one way to compute Fibonacci. And that's dynamic programming in the sense that what we're doing is we're building up the array A, and at the end, once we build it up, the solution is just A at 10. Make sense? So let's do the same kind of thing, but with recursion. So the key here is just substitute square brackets for round brackets, and you should be basically good, right? So we do something like this. And then we say, okay, so this we just substitute in. So we'll name it A so that it looks symmetric. And we'll say return A n minus 1 plus A n minus 2. Let's substitute this. That's fine as well. This is just a renaming as well. We also need the base case. So basically the base case is this, right? So we'll say if I is equal to 0, we return 0. And if I is equal to 1, we return 1. And that's equivalent, right? So basically the key here is we're doing this computation here with the square brackets. We're doing this computation here. So note that we are saying AI is equal to A at I minus 1 plus A at I minus 2. That's the same. I haven't done memoization, if that's your question. Okay. So that's now equivalent. The problem is this is not the same time complexity, right? So if you remember the last lecture from ESC180, this is actually exponential time, right? So this is, the upper bound is O of 2 to the n, 2 to the I. The exact time complexity is O of Fibonacci of I as it happens. So, however, if we just say, okay, most of what I want to be doing is just doing this computation, everything else is details, and I just want to do this computation the way I do it over here. I can do that. And the way to do it is to just do memoization, right? So I'll start with this. And I can, in fact, move the initialization to here, which I will do in a second. But for now, I'll say if I is in memo, then I'll return memo at I. And we've already done the analysis where if you do that, yeah, you will have extra calls to the function A, but not very many, right? So the amount of, so again, we've done the analysis in lecture already, so I won't repeat it, but basically the number of calls is going to be twice the number of times that you need to compute A at I minus 1 plus A at I minus 2 in this particular case. So we can transform it a little bit more. So instead of starting with memo just being empty, we can put the initialization here. So I can say 0 corresponds to 0 and 1 corresponds to 1. So I don't need this anymore. And I'll send memo around here. And now that's the same. And you can just mechanically transform one into the other, right? So this just goes here. And this goes here. And it looks like here there is a return, but really, like, if it's a function, then in math notation, like, it's literally like AI is equal to AI minus 1 plus AI minus 2. That's what return does, right? In math, that's how you would define it. So it's actually like the same line, just with round brackets. Yeah.
How did the eyes get started?
How do the I's get stored in memo? That's a good question. Like so. Sorry. Yeah, I didn't complete it. Yeah, so it's like this. Yeah.
Dictionary for
Okay. Why do we use a dictionary for memo? Couldn't we have just used a list? The answer is that in this case, we could have, and it wouldn't make much of a difference. In general, if you're solving something where you might want to skip some of the entries. So for example, in the making change problem, right? You don't necessarily want to try to access everything all at the same time. A dictionary might make more sense. But yeah, like you could have used the dictionary as well. The advantage of using a dictionary is if you don't necessarily store all the solutions for every possible I, then a dictionary is more efficient. But we haven't talked about how a dictionary is implemented kind of inside anyway. Yeah.
explain again how putting like the equal sign in the parameter works?
Yeah, so this is a default parameter, right? So the way it works is, in general, if I say something like this, then this would be 3, because by default, if n is not supplied, is 2. And this is like 6. And because if you do supply it, then it is whatever it is. So there is a funny thing where at first I didn't say memo here and it would still have worked. This is not really, so I'll tell you briefly about it. I don't really want to emphasize it too much. So this initialization actually only happens the once. So if you call the function just the once, memo is already going to be there. So it's kind of like a global variable, actually. So you can actually not pass the specific memo and it would work anyway, because there's actually only one memo. Yeah.
Same future calls, you don't pass it in again.
That's, yeah. And that's because it's just one mutable variable. So don't want to get into too much details there, because I think it makes more sense to just explicitly pass it around. But yeah, like as it happens, if you don't pass it around, like you might think that actually, well, if you don't pass it around, it's supposed to be like this guy, but no, actually it's going to be the memo that's been updated. It's not an issue over here because, of course, the value of n cannot be changed anyway. Okay. So does that make sense? Does the transformation from kind of the fib to A, does it make sense that it's mechanical? Meaning you can just do it? Yeah. All right. Okay, so the answer is yeah, true. You can do it. Okay. So the next thing I want to talk about is project 2. Project 2 is implementing seam carving in C. Here's what seam carving means. So basically what we want to do is we want to resize the input image. So the input image is what's on the left into something that's narrower, but still has basically the same, what we would say, semantic content, meaning that it should basically have the same description if you were to describe it in words. So the idea is, one way to do it is we want to remove what we call a seam from the image. So seams are like the things that are indicated in red pixels here. So it's basically a jagged line from top to bottom that you can just remove. The idea is you don't want to remove something like this, for example, because the guy is going to get squished. So that's not going to be a guy anymore. It's going to be, something weird. So what you want to do is definitely not something that's in the middle of the guy. And in general, what you want to do is something where basically the pixel to the right and the pixel to the left of what you're removing basically look like the middle. If they do, then probably what you're doing is you're removing a piece of the background. And you can kind of see that that's what's going on here, right? So to the extent that you can, eventually you run out of options. But to the extent that you can, what you're doing here is you're preserving the objects where things are going on. So for example, you're not distorting faces. Rather, what you're doing is you're like taking kind of bits of sky away and bits of the sea away until you run out of options, and then it's all over for the guys as well, although as you see, it's trying. Okay. So that's the end goal. So what you're going to do is find the best seam that you can remove using dynamic programming. So in order to do that, we need to actually mathematically define what we mean by the best seam. And that's a mathematical definition that roughly corresponds to the intuition of, I want to remove something that looks pretty much uniform and that's not going to distort objects where colors change rapidly. Right. So if the brightness changes rapidly, one example would be, like there is like skin here and there's eye here and there's skin here. So that's a rapid change. You don't want to make the seam be in the middle of that kind of thing. So, okay. So first, a little bit of notation. Just like in 2D arrays in general, we are going to use this kind of coordinate system for the locations in the image. So this is going to be like location 0, 1, and this is going to be location 1, 0, and this is location 2, 0, and so on. And this is the usual kind of thing, is we denote this as Y and this is X. So Y for kind of high, low, and X for left, right. So that's the usual kind of way coordinates work in images. By convention, of course, you could imagine doing it a different way. The next thing that we want to do is we want to take the input image and we want to compute what's called the energy. That's a fake term, basically, but that's what people call it, the energy at each of the pixels. So The energy here would be basically how much change is happening at that particular location if you move a little bit to the left, to the right, or down or up. Okay. So in order to do that, what we first want to do is compute what's called the gradient. So you will see gradients in calculus momentarily, unfortunately not yet, I'm told, but probably like in a few days. Definitely in a few days, because that's how much is left in the semester. But I will kind of very quickly tell you about it. It's in the context of ESC190, it's not actually complicated. Okay, so here's what we do. We basically want to say, if you move to the right of X, and if you move to the left of X, this is how much change you'll have in the red channel. And this would be the x-axis, essentially estimate for the derivative at location yx. Okay, so we have technically done this in 180 when we were doing velocity, but that was a long time ago. So just to remind you, so let's say that we have a row of pixels with brightness going from 0 to 255. That's the kind of images that you're also going to be working with. And it looks kind of like this. Okay, so this would be kind of dark, brighter, darker, brighter, relatively bright, and then constant color. Make sense? Does the scenario make sense? So now I want to ask, at what locations does the brightness change a lot? Right? And this is the same kind of question as if you do have this, right? Sorry, right. Trying to capture the black. So if you have this, what would it look like if I plot it? What is that? Would not have thought that. Yeah, I guess it is analog, so that kind of thing happens. Okay, so the YouTube is getting the blackboard, but you guys are not. Okay. All right, so you can imagine this being kind of like, you know, this is 10 and this is 20 and this is 50 and this is 100. So it kind of goes like this, right? So you're here and then you are at 20 and then you're back at 12 and then you're at 50 and then you're at 100 and then you are at 80 a bunch of times. Right? So you could imagine that it looks kind of like this, where this is the brightness. And this is the location. So the question we're asking, I think you can see it on YouTube. So the question we're asking is, at what locations is there a lot of change, and at what locations is there not a lot of change? So where is there a lot of change? Where, well, it's where the derivative is high. Right? So, okay. So how do we estimate the derivative? Well, one way to estimate the derivative is to just say, well, if I compute fx plus 1 minus f at x minus 1 divided by 2, that's an estimate for the derivative, right? So this is kind of like fx plus h minus fx minus h divided by 2h. We can ask, is that high or not? Right? And fx plus 1 minus fx minus 1 is an estimate for the derivative. Does that make sense? So, okay. So now we have not just a row, but we have a whole image. So let's say that the image looks like this. And just change it a little bit. Okay. So in addition to asking whether there is a lot of things going on if I change horizontally, I can also change if I go vertically up or down, is there going to be a lot of change or not? So similarly, I could ask, is f at y plus 1 minus f at y minus 1 divided by 2 is high? Okay. If the question is at xy, is there a lot of change or not? What I can do is I can just add this guy and this guy together. And I really want to add the magnitudes rather than the raw values, because I don't want the fact that there's a lot of change going left to right to cancel out the fact that maybe there is like change in a different direction going if I go up to down, right? So here's what I can do. I can say the gradient is this vector. And then I can ask, is the magnitude of the gradient high? The magnitude being just, this squared plus this squared, whole square root. So mathematically, this corresponds, this is not the real gradient, this is the estimate for the gradient. And then the magnitude, it's a little bit arbitrary that we're saying I want the magnitude meaning the sum of squares, or square root of the sum of squares. It could be something else as well. Okay, so this is all just the intuition for the actual formulas that I'm going to show. Does this make sense though? So the gradient, as you will see soon, is exactly that. If you are able to compute the exact derivatives along along the horizontal direction and along the vertical direction, you just stack them in a vector, and that's what's called the gradient. Okay. So in this case, for a 2D image, the gradient at any point is, the derivative along the x-axis, and then the other component is the derivative along the y-axis. Okay. Does that make sense? So you have done partial derivatives, I would assume. So here what you have is like the partial derivative along x and the partial derivative along y, the estimates of. Okay, does this make sense? So I'm not like teaching you calculus. This is just to give you an intuition. Does this vaguely make sense? That's all I need. Does it? Okay, no objections. So one more complication is that we actually have the red, the green, and the blue channels. So what we do is something like this. So we say, okay, so we'll compute the sum of the square estimates for the derivative along x separately for the red, the green, and the blue channel. And then we'll do the same thing, but vertically. Okay. So what we call the energy, which, like, honestly, does not correspond to physical energy, people just like calling it energy, is the square root of the sum of squares of those sums. And what this corresponds to intuitively is there a lot of change either when you go along the vertical axis, or if you go along the horizontal axis, or this is the vertical, this is the horizontal, or both? Yeah, that's right. Okay, so this is basically what that would look like once you compute it. Okay, so if you look here, then areas where there's a lot of change. So if you change from dark to bright or something, then in this area you'll see a lot of what we call energy, meaning change either horizontally or vertically or both. Our goal here, once we have this energy representation, is to find a seam that's contiguous and has as little energy as possible. So basically, we want to cut out an area that's basically all dark. And the idea is if we cut out an area that's basically all dark, then we are not distorting any objects. Because in order for there to really be an object that's distortable, you need change that when you're going a little bit to the left or a little bit up or something like that. Okay. So, all right. So once we have that, what we need to do is find the best seam. So here's an example. So let's say that the energies look like this. So this is the dual gradient image. So this is an image that was, so this would be 5 by 6. And we have those energies. What we want is we want to find a seam, so a contiguous sequence where the sum of the energies is as small as possible. So, like something like this, right? So maybe I want to go from 15 to 15 to 13 to 17 to 7. That seems like it's a cheap seam. Okay, so I want to find the cheapest one, meaning I want to take out the pixels that correspond to the lowest sum of the total energy. Okay. So in order to do that, what we'll do is define the best, so what we call the best array. So the definition here would be the cost of including this pixel as well as the best path to it from the top up to this pixel. So here the cost is 15 because this is 15 and then everything on top of it, which is nothing. Right? So then why is this, for example, 30? Well, because this costs 15 and you can get here from here. So that is why this is 30. Okay. Why is this 34? Well, because you definitely pay the 12 and then it's better to get there from 22, and 22 plus 12 is 34. Make sense? Yeah. So it needs to be contiguous, right? So it needs to, if you take and the reason, so you want a seam is kind of by definition contiguous, right? The reason you want it to be contiguous is if you start taking out pixels, from here and then from here, then the image will be very distorted, right? Because you're going to be moving like this line like this. So all the pixels move. That's not going to look nice. Yeah. We are looking for a vertical seam. Yeah. Okay, yeah.
This has to be adjacent vertically or diagonally.
Yeah, so they have to basically touch each other, so you can either go down or down and left or down and right. Yeah. Yeah.
Like the 19 to the first row?
No, so you have to it has to be an actual seam which looks like this, right? So it had so you can so I think you're asking, can I wrap around here? And no, you can't. That would not make sense. Again, you don't want to distort the image. All right. So all right. I just did this one. So the magic here is that in order to compute this one, what do you need? You need to know the cost here. So you need to know that you're paying the 22 in order to get here. And then you know that in order to get to this guy, so in order to get this guy, you need to go either through here or through here or through here, and you know how much those cost, right? So this 43 is 22. You're definitely paying the 22 plus the smallest of this or this or this. Right? So this 43 is what? It's the 22 plus plus the plus the 30. That makes no sense. So say that. 22 is sorry. So sorry. Oh, because it's 52. So this is the 22 plus the 38. My problem was that 22 is actually over here. Okay, so this 52 is the cost of getting to the 22, including the 22. So you need to pay the 22. And then you want to pay the smallest of 45 or 30 or 38. And the smallest is 30. Does that make sense? Does it not make sense to anyone? Okay. So, all right. So that's what you do. So you compute this array. Once you've computed this array, how do you know what is the smallest cost possible seam? Anyone? So the total cost for the whole seam, what is it? Yeah. Yeah, the minimum of the bottom row here. Yeah. So the smallest cost is apparently 62. Does that make sense to people? So in order, someone is saying no. So in order to get me the smallest possible cost, I need to end up at one of those pixels. This row corresponds to the total cost of going down to this pixel and paying the 17 plus the least cost path to 17, or going down to this pixel and paying this 17 and also the least cost path to this 17, or going down to this pixel and paying for the least cost path to that as well. And this seems like the cheapest. Yeah. Yeah, exactly. Yeah. I mean, it's also dynamic programming. Right? So that means that if I can find the smallest number here, I know the location of the last pixel in the seam. So this happens to be this. And then I know that if the seam ends here, then it must be that, meaning here, it must be that it went through either here or here or here. And I can just, again, look up the smallest cost over here. So it must be that I'm over here. Right? And then again, look up the smallest cost. So it must be that I'm over here. Look up the smallest cost. It must be that I'm over here. Look up the smallest cost. It must be that I'm over here. Okay, and the smallest cost needs to, so it needs to be that the second to last pixel in the path is adjacent to the last pixel. So you only pick from this or this or this. Yeah.
Why'd you go to 58 instead of 55?
My mistake. Okay, sorry. Yeah. So yeah. That's why you need a computer. All right. So that's the recovering the seam. Like you saw in the lab, you can actually do something that computes the least cost path simultaneously with computing the cost array, but we're not doing that. Okay. So that's the assignment. And of course, kind of the goal here is to do another example of dynamic programming as well as practice with C. It is in C. Yeah. Yeah. Say it. So that is actually not a requirement. There is a remove seam function. Oh no, sorry. You are actually yeah, I did put it in. Yeah. So there is a remove seam as well. All right. So okay. So you will see today or tomorrow in the lab how to work with the image objects in C that I've given you. So that you will see in the lab. As well in the lab, you will see. So I didn't talk about it, I guess, yet. But people always ask, like, how do you make the animation? And I usually said in the past, well, it's kind of annoying and complicated, so I'm not going to show you. You can look it up. So trying something new this year. So the answer is ask ChatGPT. So the way it works, and like you kind of probably need to know this. So the way it works is that this is what's called a GIF file. So GIF files can contain animations. The way animation works is it's just a bunch of images called frames that are, in a sequence. And then you're just displaying them fast. And then that's why it looks like a movie. If you didn't know how movies work, that is how. It's a bunch of frames. So what you need to do is basically create a bunch of frames and put them in the GIF image, and it can play the animation. How do you do that? Well, ask ChatGPT, it'll tell you. So there is a first question where you're practicing with getting an image be brighter or darker. So you'll practice with kind of input output for in C actually. And then you'll switch to Python and do the same thing in Python, so in order to make the image brighter, of course, all you need to do is just multiply all the brightnesses by a constant. So the way I think probably everyone already probably has practice asking ChatGPT for stuff. I think common experience is that if you ask for too much, it'll give you something, and it might even run on some hypothetical computer. It might not run on ECF, especially with image libraries that you need to install and stuff. Some of them work, some of them don't. If it gives you a big chunk of code, it's difficult to debug. Although sometimes it works right away. I can't guarantee that if you just don't plug the whole thing in, it won't give you something that you can run right away. That's completely possible, but not reliable. So what I suggest is kind of step by step, having some kind of plan, which is, figure out whether you can read and write images in Python first. That's not difficult, especially if you tell it that you want to use PIL. PIL is a library for manipulating images. So it'll just tell you how to do that. It'll tell you how to do what you did in question 1, where you made an image brighter or darker in C. And then just make sure that you can write an image to the disk and actually find it on the disk. So one issue that we always encounter with files is it writes it somewhere, you don't actually know where it wrote it, or it tries to read it from somewhere, which is not the folder that you opened, whatever. So the idea here is maybe if you write something that's very big that ChatGPT just gave you, you won't even be able to know where it saved it. So just make sure that you know where it saves things, then ask it for a series of images. Just ask it to put it into a GIF file. That's really not difficult. It's like 2 lines. And then you'll be able to create the animation. Yeah, we'll see how it goes. And then, so the lab is pretty short, and you can just start working on project 2. All right. Do people have questions about any of that? All right. Yeah, I think like half of you have the lab now, so might as well just start on that. I'll see you on Wednesday. Bye.